Assalamualaikum class, hope you're all doing well. So in today's lecture, we will continue off with the graph algorithms. Previous lecture, we learned about Kruskal and Prim's algorithm, and there we created a minimum spanning tree from the graph. Here, we are going to find the shortest path between the nodes in the graph, which may represent, for example, road networks. It was first conceived by a computer scientist named Dijkstra in 1956 and published 3 years later. The algorithm exists in many variants. Its original form was found to find the shortest path between the nodes, but more common variant fixes a single node as the source node and finds shortest path from the source to all other nodes in the graph, producing a shortest path tree. So the Dijkstra algorithm is a solution to the single source shortest path problem in the graph theory, just like we learned in the Prim's algorithm. It works both on directed and undirected graphs, however, all edges must have non-negative weights. Unlike Prims and Kruskal, which worked on undirected graphs, here we can work on both. Its approach, as we learned before, is greedy, and the input is a weighted graph with edges and vertices and the source vertex, such that all edge weights are non-negative. Output हमारे पास क्या आएगी? Length of the shortest path or the shortest paths themselves from a given source vertex to all other vertices. So in practice, the Dijkstra algorithm is used when we want to save the time and fuel traveling from one point to another. So in case of Prim's algorithm, it is used when we want to minimize material cost in constructing roads that connect multiple points to each other. And the Prim algorithm can handle negative edge weights. But in the Dijkstra, it may fail to accurately compute distances if at least one negative edge weight exists. And both can work on directed and undirected graphs, but Prims can only work on undirected graphs. So this algorithm will find the path with the lowest cost between the vertex and every other vertex. So example here is that the vertices of the graph represent cities and edge paths. Cost represents driving distances between the pairs of cities connected by a direct road. So the Dijkstra algorithm can be used to find the shortest route between one city and all cities. So the working of the algorithm is that we have to start with the decided vertex and then continue on to the others. So first, we will initialize all the distances with infinity because we have to discover all the paths as we move along to the shortest path. So here we are starting with A, and to reach the A point, we have to travel what? Zero distance. So here we have written 0, and we have a set. We will include all the vertices which are connected to the graph. Moving on, we have two paths. One is leading to B and other is leading to C. And we will update the table and we'll find the shortest path to it. Here the shortest path is 3, which is going towards C, and we will add A in the set. So choosing between B and C path, we will choose C. Moving on to C, we have further 3 more paths to B, D, and update the table, just like we did in Prims. And we will write B, we have 3 plus 4, we got 7. Then we got 3 plus 8, 11 to D, and 3 plus 2 equals to 5 to reach the E point. So before we chose A and C, now we will choose the shortest path. Here with the shortest path have E, we will choose 5. Moving on, now we have another path to D, which is 5 plus 9 which is 14. So already we have a D which computes up to 11. So we will not update into the table. We will not choose that path. Here we have 7 and 11. So further on we will choose 7. Indirectly from we will reach up to B point. From B we have 2 paths to C and D. 7 plus 1 is 8. We already have 3 to reach the C, so we will not update. Further we have 2 plus 11, which is 13. So we will not operate it. We already have 11 from A to C. Which path we will choose? We have A to C, which was 3, then C to E, which was 5, then C to B got 7, then B to D, which is 9. And there we have all the vertices, including the set. The Dijkstra has several real-world use cases, some of which are as follows. Here we have mentioned traffic information systems are more prominent. Like we have used it in Google Maps, the digital mapping services, and these encounter the shortest path algorithms, and where we find various routes of path connecting them, but it has to show the minimum distance. So the Dijkstra algorithm is used to find the minimum distance between the two locations along the path. And here they have mentioned mapping like MapQuest and Google Maps and routing systems. Other application would be like social networking applications, in which many applications you might have seen the app suggest a list of friends that a particular user may know. So how do you think many social media companies implement this feature efficiently? So the standard the disk algorithm can be applied using the shortest path between users, measured through handshakes or connections among them. And another usage, say telephone networks, in which the bandwidth represents the amount of information that can be transmitted from the line. So if you imagine a city to be a graph, the vertices represent the switching stations, and the edges represent the transmission lines, and the weight of the edges represents the bandwidth. So you can see it can fall into the category of shortest distance problems. So it is widely used in the routing protocols required by the routers to update their forwarding table. The algorithm spied the shortest path from the source router to the other routers in the network. So that's it.